So now that we have the forces, London dispersion, dipole-dipole, hydrogen bonding, we are going to start using those concepts to start explaining how liquids behave. Especially today, we are going to start looking at how liquids evaporate and why do they evaporate, and how we can determine why one liquid will evaporate faster than other, why alcohol evaporates faster than water, why oil takes a long time to evaporate. And the lab goes hand in hand with part of this. So in here, we'll give it some definitions, and we're going to try to quantify that mathematically today. And then in the lab, you will put it to practice, and you're going to compare different liquids and see which one evaporates faster. And then you'll be able to explain why things evaporate faster than others and what is going on. So let's start by looking at why does nail polish remover vanish while a puddle of water lingers? So just because it's a liquid doesn't mean they're all going to evaporate at the same rate, at the same speed. Some evaporate faster than others. So there's has to be something that's tied to that evaporation, or a property that can explain what's going on, and we're going to call that vapor pressure. So when we have a liquid, we have particles in the liquid, and then we have a gas phase on top of that liquid. The molecules of the liquid are going to try to escape into the gas phase and start evaporating. How fast or slow depends on a few factors. So evaporation or vaporization is the liquid turning into a gas, but for that liquid to turn into a gas, we need a certain amount of energy. That energy is a delta H that is greater than 0, so it means it's endothermic. So you need to add heat to the water for that water to start evaporating. And temperature is going to be one of those factors that are going to determine how fast or slow liquids are going to evaporate. But the other factor is going to be the intermolecular forces. For example, we have methane, which is a liquid, and we have water. Methane is a nonpolar molecule that only have London dispersion forces. Water has much stronger forces because it has those hydrogen bondings. So water is going to have a higher delta H of vaporization than methane because of those type of forces. So it requires more energy to pull the water molecules apart than it is to pull the methane molecules apart. Again, you have to be able to identify those forces in any type of molecule I gave you, and you should be expert by now on how to do. So if you're still confused on how to do it, please reach out, because this chapter 11 is all about forces. Okay, so let's look at a closed system first. In a closed system, we have a liquid. We don't have it open to the environment, so that liquid is coexisting with a gas. As time passes, some of those liquid particles are going to start evaporating and going into the gas phase. So the amount of liquid decreases with time, and the amount of gas increases with time, as the diagram is showing you in here. That is going to continue until an equilibrium is reached. What this equilibrium is doing is saying that the rate of evaporation equals the rate of condensation. The rate in which particles are turning into a gas and the rate into which particles of gas are turning into a liquid is the same. The same amount of particles are turning into a gas, the same number of particles are turning into a liquid. So it's an equilibrium between those two phases and the amount of particles. And you'll see that after this first module on forces and solutions, we're going to get into kinetics that explain how fast and slow those rates are. So we'll look at those rates later on. That's not part of the scope of what we're doing right now. Now, that tendency of particles to escape the liquid depends on pressure. And we say it's equilibrium vapor pressure. We're just going to call it vapor pressure. And it's a direct measure of the tendency to evaporate. So high vapor pressure is how many particles have escaped into the gas phase. So how many particles are going from liquid to a gas? The less particles are moving into a gas, the less volatile that liquid is, meaning that less evaporation is occurring. So the more particles are turning into a gas, the higher the evaporation is happening, the higher the vapor pressure is. So vapor pressure measures how many particles are escaping into that gas. We have to, well, I already mentioned there's two parts to this, temperature and forces. Strong forces are going to cause the liquid particles to escape at a lower rate because they're trying to stay together. They don't want to escape each other. They want to hold hands together. So those, let's say, water particles are going to try to stay together. They don't want to go to the gas phase. So stronger forces, less vapor pressure. Low forces, higher vapor pressure, because lower forces, those particles can escape faster into a gas. They won't be able to hold hands as strong as they want, and they can escape faster. So more volatile, more evaporation, lower forces. And that is something that you're going to try to prove today through the lab. You're going to compare different liquids and see which ones evaporate faster and why, based on the type of molecule it is and the forces that are at play. Now, temperature is another factor. Higher temperatures means higher vaporization rates because particles move faster. If they move faster, they have a higher tendency to escape. Lower temperatures, lower vapor pressure, lower tendency to escape. So two things happening in here that you have to take a look at. Now, let me see what's coming next. We can do this mathematically. And to do it mathematically, we have to take into consideration the pressure, the enthalpy, energy, and the temperature. And we can do a graph of the natural log of pressure versus delta H over T. It should be a direct relationship. It's a straight line. But looking at it this way doesn't help you a lot. So what we're going to do is introduce this equation called the Clausius-Clapeyron equation. It is the natural log of pressure 2 over pressure 1 equals the delta H of vaporization, which is a heat of vaporization in joules per mole. It's a given value, unless I ask you to calculate that. You have an ideal gas constant, which in this case is going to be 8.314 joules mole Kelvin, which is different from the ideal gas law constant that we did in Chem 1 with gases. It was 0.082, if you remember. Yes. Heat of vaporization. No, it's a delta H. That's the constant when you're calculating heat. This is a different one. So then you have the T1 minus 1 T2. This is a derived equation. You don't need to know how it is derived. All you need to know is how to use it. You don't even have to graph it. So what you're gonna see is, it's gonna ask you, well, I have two examples coming up, but you need to be able to solve for pressure 2, pressure 1, T1 or T2, or for delta H of vaporization, what heat is needed for that vapor pressure to start occurring in your system. So let's look at some concepts in here to make sure that we know how to define it, and then we'll look at the examples. So we are used to talk about boiling point. So what is boiling point? It's the temperature at which the vapor pressure equals the atmospheric pressure. So things don't start boiling until the pressure in the system equals the atmospheric pressure. So that water that you have in the stove and you start boiling starts as a liquid, temperature starts going up until the pressure equals the atmospheric pressure. Once that happens, you're gonna start seeing bubbles forming throughout the whole liquid. Now, we also have this thing called normal boiling point. The normal boiling point is the boiling point at 1 atmosphere. It's a very specific value. And there are graphs that you can have. Pressure and temperature. So if you do it at 1 atmosphere, you can read what the boiling point temperature, the normal boiling point is for any particular substance. So these are different substances. So if I give you a graph, I can ask you what is the normal boiling point, let's say, of acetone. Go to the graph, look for the graph line of acetone, look for a pressure of 1 atmosphere, read the temperature, that will be their normal boiling point temperature. That will be different for that particular substance boiling at different locations. So you can go boil your water at sea level and then going to the top of the mountain, the boiling point is going to change. It's not going to be 100 degrees Celsius always, because it has to deal with the pressure. Okay, let's see. Okay, so let's look at this example here. I have butane that has a vapor pressure of 764.5 millimeters mercury at 0 degrees Celsius. And at 9.9 millimeters mercury is minus 78 degrees Celsius. Calculate this heat of vaporization, the delta H vaporization. So because you have pressure 1, temperature 1, pressure 2, temperature 2, and it's talking about delta H vaporization, you know you're going to have to use the Clausius-Capron equation. By the way, you don't have to memorize the equation. You're going to have a reference table that has equation in it with a few other things. So you just have to set it up. Plug in all the values you have. I do recommend that you list everything you have so you know exactly what is what. The 764.5 goes with 0 degrees Celsius, and the 9.9 goes with minus 78 Celsius. Just remember, you have to convert Celsius to Kelvin. We don't use Celsius to any mathematical calculations in chemistry. Everything has to be in Kelvin, especially because that R constant is in Kelvin. So you have to substitute and solve for delta H of vaporization. So you have to calculate the natural log of 9.9 divided by 764.5, then multiply by 8.314, and then the answer from this parenthesis calculation. It's going to be around 24.7 kilojoules per mole. So make sure that you can plug in the numbers into the equation and you can solve it. You will have at least one problem using Clausius-Clapeyron. So I'll leave it there for a second so you can. Yes.
I just have a question. What is the difference between heat of vaporization and the boiling?
Heat of vaporization. The heat is just the heat needed for that liquid to start evaporating. But heat of, vaporization pressure is the pressure. Well, they're hand in hand. Is a pressure for the liquid particles to start going into a gas.
Like, but for boiling point, like what is the difference?
Boiling point?
Yeah, like what is? I'm just confused on what exactly it is.
Boiling point is the temperature. The temperature goes from liquid to gas.
Okay.
Which goes with the vapor pressure. The heat of vaporization is the heat that you have to add for that to start happening.
Okay. Okay. Thank you.
Okay. You okay, Liam? Okay, you had a puzzle face. Okay. Alrighty, so you have a second one. And this one is different because I give you the delta H and I ask you for one of the temperatures. So now you have to solve for temperature. So it's a little more math involved. So liquid mercury has a delta H vaporization of 59.11. Its vapor pressure at 0 is 2.3 times 10 to the minus 7 atmosphere. Calculate its normal boiling point. So delta H is given. P1 is also given. T1 is also given. Now it's asking you for the normal boiling point. So it's asking you for T2 at the normal boiling point. So if it's asking for normal boiling point, it has to be at 1 atmosphere. That's by definition. So you have everything you need but T2. So we substitute. Solving for T2, I'm skipping a lot of steps. I know that. So I'm leaving up to you how to go from here to the answer of 612 Kelvin. Remember, as you're substituting, make sure those units cancel out. That's the best way to know that you set it up correctly. Next week, because I think we'll finish the theory a little bit early in the class, I'm going to bring a set of problems that we're going to use to practice. Yes?
Finding that answer, I was just asking if you could go through how you isolate to solve it, because obviously I know how to substitute in things. Like, if I were to go solve it on a calculator, like I can't.
How to solve it? So you put natural log, parentheses, 1 over this one. Then you have to multiply by 8.3414, divide by 59, 110. And then you can multiply like this. You can simplify this, or you can multiply whatever you get by this and then subtract, and add it. Okay, I think I better do it on the board. I don't have my calculator with me, which I should start bringing out. So let's say this is X If that makes sense. So you just sit down with it, try it yourself. The lateral log is the only thing that might give you some trouble in the calculator, just because depending on which calculator you have, sometimes you have to press the natural log key first and then the parentheses. And in other calculators, you have to put the parentheses and then hit the natural log. So depending on which calculator you have, make sure you know how to enter it. You'll know because you'll get the correct answer. If you have problems, it's not coming out, please let me know. From now on, I'll do more steps than just set up an answer to make sure that you know how to do it, especially as we go through the kinetics and acid and bases, you'll need to know how to do it. So it's my fault trying to save some time, but I'll add the steps from now on to make sure you know how to do it. So now you can take any liquid and compare it to another liquid. And in terms of forces, you can explain why one evaporates faster than the other. Or mathematically, you can try to calculate what the boiling point of that liquid will be if you have enough information using the Clausius-Clapeyron equation. Again, you don't have to memorize the equation. I will be providing that as a reference and still working with how those references are going to look for you guys, because I don't like the way I did it the last time, so I'm just going to change the look. I'll have that ready by next week for sure. If I have it earlier, I'll post it and you'll see it. I think there's some references already in there on Canvas, so you can look at what I have.